Hey, Steven.
Hello, how's it going?
Living the dream. It was a lovely day today.
Yeah, is it ever? That drive is getting pretty bad.
Yeah, I didn't have to go into work today and working from home, but I had to go out for a bit just in and around Kitchener, and there was a whole bunch of just small little accidents. It got greasy at about 1 o'clock.
Yeah. Yeah, that's a slow drive home for me.
All right, so the recording started. Perfect. Okay, I haven't gotten around to looking at all of the quizzes yet. Were there any? But there were a bunch of emails about issues with people connecting into the VMs. Here, I'll turn this on because Steven's on. So, and then being able to access the software. So there was a few complaints that the VMs you guys were connecting into didn't have the required software. The few of you who got me the computer names, I logged into those machines and the software was there. So I'm not sure what the issue is. I mentioned this last night in the other class, but I phoned IT and I don't know if I got one of the people who've been there forever or somebody who's a student doing a rotation in IT. And they've assured me that as long as we're using, let me share my screen. So as long as we're using the Cambridge open access machines, that the PLC software is on these machines. So none of the other ones will have them that have remote access. There are labs at the college that do have the software that are not accessible remotely. So if you log into a machine and it doesn't appear to have the software that we need, please just confirm that you're on one of these Cambridge open access machines. Take a screenshot of the name of the computer, because I couldn't find one in the Cambridge open access list that didn't have the software. That being said, I have had a number of issues with the software on the machines, but that is a different animal, which you guys witnessed last night. So any questions beyond technical issues with connecting in? Okay. So tonight I'm going to go through my presentation. Then I'm gonna run through the lab that is on the D2L. I'm hoping to get that done in about an hour and give you guys 2 hours to go through the lab yourselves while you're either connected in here. If you feel you're good and you want to do it some other time, that's great. I'm gonna stay connected with the meeting open and on one of these machines for the duration of the class until about 9 o'clock. I may or may not turn off the recording and see if I can push my lab demonstration and whatnot onto YouTube beforehand. But that's the plan for this evening. So let me get this. And I believe, yeah, OU came in. So the participant who was B, I'm sorry, is that Baruch? You can either say yes in the chat or. Okay, perfect. Sorry, bear with me. Got too many windows open here. Okay, so I'm just reading Olu's comment here in the chat. So week 1, that lab, it's not marked. So the idea was that you guys could send me a photo just to prove that everybody was able to get online in the simulation world. But there's no marks associated with that. The marks are on the quiz. So submit the quiz. And don't worry about the Dropbox for last week. It was just kind of making sure that the technology is working for everyone. And if we do have some more technical issues, try to get things going tonight, and I'll be here. I can try to walk you through connecting in and get everything running. Okay, I'm gonna have to turn my video off because my internet connection is just dying. Sorry, guys. I'm sure you'd love to watch me struggle. Okay, perfect. All right, so this week, B, there's B is back. So B, our attendant who is in B, if you could just type your name in the chat, I can update your name. All right, you quite so is. Oh, it says I can, but it isn't letting me. All right, I've updated the attendance list accordingly. So thank you very. Oh, there we go. Wow, I have too many monitors open. Technology is a pain. Perfect. So this week we're going to cover Boolean addressing. So Boolean is the first of many different types of data types. And if you've done programming before or electrical engineering, even some puzzles, Boolean logic is a very common topic. So if this, then that. So for PLC, Boolean logic is what ladder logic is. So on or off. Boolean is a data type used in the industry. It's the same as bit. So when we were talking about bits and bytes, individual bits outside of integers and double integers are bools. So we'll see that. And we're going to cover some of the Boolean operands found or operations found inside PLC programming. How to control discrete outputs using some common instructions found in the PLCs, and how to apply Boolean logic in a PLC program. So as we covered, it might have been in the other program, but as the other class, sorry. So a Boolean at its most basic form is a 1 or a 0, on or off, true or false. So with Allen Bradley, it's all 1s or 0s. If you're using some other controllers, sometimes you'll see true and false, on or off as words to signify the state of Boolean operands or Boolean data tags. So a state of 0 typically denotes false. So this button here is not pressed, so it is false. It is 0. If it were attached to a digital input, the circuit would not be closed for a normally open switch. And a state of 1 typically denotes true. So the same button, a normally open switch, when pressed, becomes true or 1. Again, these buttons are normally open. So example of Boolean logic for this circuit is the circuit is currently open. So because that switch is 0, the circuit cannot close. We want to turn on the light. So if we complete the circuit by closing the switch, we're creating a true state at the switch, which will close the circuit and turn the light on. So if you have ever done electronics, wired up circuits, and know how switches or even relay logic works, the logic inside ladder logic is very similar. So Boolean logic can consolidate several binary signals down to a single controlled output. So the example before was a very straight through with that switch. If the switch is true, then the light turned on. So if the input is true, the output is true. So there's some very basic Boolean operands that most people will be familiar with, even if you've never heard of this. That is and, or, and not. So Boolean operands can be used together to create equations. So, and then Boolean operands you'll see exist in other types of circuits. So if you've used or done any electronics, if you've troubleshot or looked through the manuals of many pieces of equipment, if you've ever read your refrigerator manual, they're going to have circuitry logic in there. A lot of the symbols that you're going to see in that are Boolean logic, switches and gates. PLC programming is very similar to that. So the and operator, it outputs a true signal when multiple signals are true at the same time. So if you've ever, again, the electrical symbol for an and is this would be called either an and gate. You have the 2 pins inputs on the left. The 2 pins on the left are the inputs, and the pin on the right is the output. So I thought there was animation on this, but for this case, both of these inputs would have to be true for the output of this gate to be true. So that would be Boolean. The Boolean logic for this would be 1 and 2 for output to be true. Does this make sense? There are more examples, and I will make this make sense with ladder logic soon. So OR. So the output for an OR is true when one or more of the signals are true. So this is the OR electrical symbol. So again, it's showing two inputs on the left and an output on the right. So with the OR, if one is true, the output is true. If only two is true, the output is true. If 1 and 2 are true, the output is true. But if neither of them are true, the output is false. And then the not operand is the output is true when the input is false. So it's essentially a reverse. If the input is on, the output is off. The input is true, the output is false. If the input is false, the output is true. And the not symbol, you can see in a lot of electrical symbols can be shortened down to only this circle. So you can see and or gates with a not symbol attached to the output side to indicate special cases for NAND and NOR gates. But for the purposes, we're just going to work with and, or, and nots right now. So Boolean equations, which you may have seen elsewhere, again, in puzzles, electronics labs, electrical circuits, would look like this. So this is an example of an equation where we have an OR gate and a NOT gate running into an AND gate. So the breakdown of this equation is D equals A or B and not C. So while A or B are true, which would turn the output of the OR gate to true, and C, to get the output of this gate true, has to be off for both of the inputs for the AND gate to be on to turn D on. That's a little bit of Boolean logic acrobatics. Does that make sense? Does it not make sense to anyone? Perfect. So bits, so remember, going back to bits are Boolean. So to store ones and zeros in the PLC information, they are stored in physical areas of the memory. So the area of the memory could be indexed, and it could be then referenced to internal addresses. So this sounds more complicated than it is, but the processor can refer to many internal addresses as different things. So 040, which we saw last week in some of the documents, would indicate an output, could also be referenced to internal memory that could be used for motor run as a tag. But they're still Boolean because the output is either on or off, and motor run as a tag could also be on or off. They could be equal to the same thing, but they're just bools, on or off. Digital points, bits. It's all the same. So that's why we started with what bits and integers and bytes were, because a lot of ladder logic boils down to manipulating logic and information at the bit level. So we refer to the simplest form of data as a bit, which is a portmanteau of binary digit as a logical state with two possible values. So in a control logics, a single bit would be a bool data type. And then as we covered in fundamentals, we learned that bytes and integers are made up of a number 8, and then full word integers are made up of 16 bits. So bringing this back, so the Boolean logic into ladder logic. Why did we go through that before? We can write our own Boolean equations in ladder logic. So remember, PLCs, they scan logic in a particular order, left to right and top to bottom. So rung 0 is our light enable. So from our example for the Boolean logic, when A is energized, the light is turned on. So when the input, the button, or in this case, I610 becomes true, the output of that rung, 030, becomes true. So that's a straightforward if this, then that. So now rung 2 is a new light. So now we have 2 bits, 2 normally open bits or switches in series. So if we're thinking of this as an electrical circuit, and you may notice if you've ever read motor starter circuitry, you might notice that this looks very similar to contacts of a relay and coils of a relay. So it was designed to mimic your motor starter logic here. So with rung 1, we have an and statement. So when A and B are energized, so remember ands, so when 030, where's my pointer, is true, and I612 is true, then 031 becomes true. So now this is our AND gate. So A, B, output. That makes sense? And so now the next rung is another light. So you'll notice that there's a branch. So there's this parallel path around this bit. So these branches are OR gates. So you can see here that we have when A and B are energized, then the output will turn on. So when 61.0 and 61.1 are true, the output will turn on. Or when C and B are true, then the output will turn on. So that's that same Boolean logic before. If A or C and B, then D is true. So when A and C are energized, but not B, then there is no output. Make sense? There has to be a path from the left side of the ladder logic to the output for the output to become true. If one of these, if there's no, and you'll see with the light on, you'll see, sorry, when the processors are running, you'll see, oops, sorry, that's my VM. When the processor is running, you can see the state of each individual bit based on this green highlighting around. So that means that that bit in this case is true. So because this is a normally open contact, then this bit is on, and then it's passing data through. And the next rung here, you can see that these are actually normally closed. So these are your not conditions. So when we move down, oh, so the last rung here, the light is energized when push button A is not energized, push button B is not energized. So, sorry, that is when a light is energized. Sorry, this data, this is typed up funny, and that phrasing is a little confusing. So 032 is this output here. So when 032, the output of this this light is on, and I610 and I614 are both false, then the output will turn on. Does that make sense? This is typed a little funny, and I'm going to make a note to try to fix that. So imagine if this were a different switch instead of being another light, but it's the output of the rung above it. When it is true and the two inputs are false, the output of this rung is true. So these are your not gates. Does that make sense? Does that not make sense to anyone? Great. Okay. So a brief recap. So we saw in the previous scenario, multiple Boolean inputs can be used to control a single output. So we want a light to be on when either the push button is pressed, or a proximity sensor is tripped, or a weight sensor is tripped. Whatever input or ever condition in the logic can be used. It doesn't have to be buttons. So this light is on. Sorry, the light is off currently, and then we want to turn it on whenever a push button or the proximity sensor is tripped. So if either one of these conditions is true, this output is true. So that's an OR. So one of the things that we need to, and you might be tempted to do here, is you might think you can do this in 2 rungs, but because of the way the code executes, this may not work for you, because you can't, it will scan the output, and if the push button is depressed but not the proximity sensor, the light won't turn on, because this may be true, and in your logic you would think this bit would turn on, but because on the next rung the proximity sensor is not true, it would be turning it off in the same scan. So if you write to or try to control the same bit from two different locations in your code, you can really run into issues where things won't turn on when you think they should. So this is something that the code will flag for you, and I can show you where it'll flag it. It's called destructive referencing. So an OTE should only be used once inside your logic. Does that make sense? This is something you will do. I still do it every once in a while, just thinking, programming faster than I can think. Again, the code will throw up warnings for this. So last rung wins. So whatever is happening further down the line is the last state that this bit bool will be in. Again, this is just reiterating what I said. Last rung wins. This means that rung 1 will always fight with rung 0 for control. When rung 0 wants the light to be on, if rung 1 wants the light to be off, it will be off. So this is not an or statement. This is bad practice. Any questions? So some best practices for Boolean logic is reduce complex logic to its simplest form. If your program is starting to look too complex, there's a chance that it can be simplified. So one of the things that is really good to do is write down a narrative of what you want to do. And this is a document. When I say narrative, control narratives are the programming guidelines to systems. Whether it's even in the lab where it says program this to do that, even if it's something as simple as planning out where you're going to turn things on from, it can really help simplify and wrap your head around your code. So, for example, we want rung 3 to be active when all logic in rung 2 is active. Instead of duplicating the logic from rung 2, we can just use the output from rung 2. So, oops, you can see here, we want output 3 to be on when output 3 is on, but not the switches. So instead of copying rung 2 and doing the same thing again, but then just adding additional logic to it, we've already boiled down, if you will, we've already evaluated this condition. Let's use the output of that condition as a stepping stone for the next condition that we need. It won't always work, but a lot of the times it can, especially if there's a very linear logical progression to your code and you don't need it to step back to a different state. Build on what you've already done. Don't start from scratch when you've already done half the work somewhere else. Structured text example. So Boolean logic in a different PLC programming language. Again, it's all very, very much the same. If the pump is running, so while pump is running and not pump fault, do fill tank equal 1. So if true, if the pump is on and the pump isn't faulted, fill tank equals 1. So fill tank is a bit, is a bool. All of these would be bools. And fill tank could be triggering another function of code. Fill tank could be running a pump, or it's even just saying it's in the state of filling the pump or filling the tank. Does that make sense? So AND gates and logic is used to turn an output on when 2 or more things are true. So it might not be 2 things, you might have to have a number of them. That's going to be adding them in series in your ladder rungs. An OR statement is used to turn on an output when either 2 or more things are true. So that's going to be your multiple branches. So those parallel rungs around contacts or other bits of logic, those each branch is an OR statement. A NOT is used to flip instructions, energize and de-energize states. So if you have a fault state and you want to do something when a pump isn't faulted, or you want a machine to cycle a cylinder when there isn't something in its way, or clear a plate of debris when the weight sensor isn't triggered, then you would use NOT statements. So yeah. So the examine on and examine off instructions are the building blocks of ladder logic. So that's those 2 lines. The one that looks like a normally open and the other one with the normally closed. So that's the we'll see it. And then for ladder logic, for any processor that you're going to use, PLC, even most microprocessors and programming languages, the last line of code wins. So if you tell something to turn on and off a whole bunch of times in your logic, and the last thing it does is turns it off, the output for it is going to be off. So you've got to pay attention and map your code out so you're not trying to turn too many things. You're not trying to do something twice to the same bit of information. It just won't work. And then you'll scratch your head and wonder why your code doesn't work until you can step through it. Any questions? Perfect. All right. That's the presentation. And like I said, I'm going to jump in. So I've already connected into a VM. Do people, is everybody connected into a machine right now? Do you want some time to connect into a machine before I get started? Or would you rather me run through this and then worry about you guys connecting in? Yes. Which one, Martin? I'm sorry. You're connected in? Give you some time? Okay. I'm gonna go. All right. I'm gonna give you guys 5 minutes to connect in. I'll go grab some more water and I'll be right back. Sorry. So to connect in, we need to make sure we've downloaded the Conestoga configured Pulse Secure VPN client. And then we've added the VPN Conestoga c.on.ca. It's important that you do install the one from the website. So there are documents in D2L about connecting in that guide you through that process. It has to be the one from the Conestoga website because it has some pre-shared keys baked into the background. Without it, you can't connect in. Once you've connected in, you navigate to this list of machines. It's the remote access section on D2L. And then we're using the Cambridge open access machines. So this list will update as they become available. There's 30 to 40-ish computers available when nobody's logged in. I've seen it as low as 1. So this depends. I think there's a bunch of night classes happening, so they get used up. Once you download these, they'll show up in your download folder. So this will trigger an RDP link to the different machines. You'll double click on that. It will open up a remote desktop session. You'll need to log in using your credentials, which we did last week. And that brings you to these open access machines. Sorry if you are hearing my daughter. So she has no volume control like her father. So I'm running just off to the side here. This is the lab document that you'll find in this week's D2L called Lab 1. There's the PowerPoint presentation as well as some additional reading documents that just reiterate everything that I said and are in the slides. And then the lab Boolean addressing. I'm not going to bring it back and forth a whole bunch. I'm just going to kind of work with this off to the side here. But do go to the Alan Bradley lab tips templates and download the ones that it recommends for connecting in, especially if you're having problems. And you do need to download, these are the same files that we downloaded last week. So the A2148 lab simulator, the ACD file, that's your PLC program. The APA file, that is your graphical interface program. And then I found this kind of helpful. So if you're having issues connecting into anything, one of the other teachers has a troubleshooting interactive instructions for configuring things and navigating these computers. If you're having issues and rewatching me do this isn't helping enough, and you're trying to do this outside of the class, please look at some of these tips. They're what I use to figure it out. So they do work. So when you download sorry, I ran through this earlier. So when you download your files to your computer, you can just copy and paste them right onto the desktop. So that's the PLC program, and this APA file is your graphical interface. So if they don't show up as these images, you might be on the wrong machine. If you don't have a folder on your desktop that says Rockwell software, again, you might be on the wrong machine. So once you've pasted those in, launch or open up this folder and then launch Studio 5000 Logic Emulate. I double clicked on it, but I already have it launched. If nobody else has been on that machine that day, it opens up like this with the processor configured in slot 0 and your links driver configured in slot 8. If you don't have it configured this way, somebody's put something else in slot 0. There's a couple options. So you can either add devices in yourself. So if you pick a slot and go create module and wait for it to take forever. Emulate 5570 is the emulation controller, and just make sure it's going in one of the free slots, because I clicked on slot 3 before I went to add. It'll automatically choose that one for me. I haven't seen any use for the input simulation, but if you have to have communications between different processors or have 2 different PLC programs you're working on, this will run up to 15 of these processors in emulation mode. And you just need to make sure that you select the right version. Everything I've seen us doing is version 30. And then I just use the default for that. And it will load in a controller. It's sitting there with no program in it, or at least an emulation program, and you can then download to it. You could do the same thing if there's nothing in slot 0. So starting with the visual interface, double click on it. What it's doing here is it's actually launching the application manager. So this APA file is a backup of the program. It's the only way to transmit or move these programs from machine to machine as a single file. When it opens it up as a project, it's actually a whole bunch of files all over the place, so you have to back them up. So to use them, you actually have to unpack them. That's what this ME application manager does. So you select next, you enter in your name. So in the lab tip, I think it says to put your name and a number. I don't think it matters what you use, as long as you read, when you're submitting files to the Dropbox, as long as you're renaming your files according to what the document and the like the D2L is looking for, you can rename these whatever you want, really. I'm gonna go with Ryan 0 and finish. So it'll look like it does nothing, but it has done something. Now I'm gonna launch my PLC program. And wait. Okay, my PLC program was already open. I thought I'd close it. So now to access the interface, so we actually want Factory Talk View Studio. So you can either access it through the Windows folder like I've done. You can type in Factory Talk View Studio, or again, all of your software in here for Logix. We want Factory Talk View. And we'll launch Studio. The Studio will open up and give you an option of Site Edition. We want Machine Edition. Machine Edition is specifically for Allen Bradley's touch panels, and these emulators have been programmed in the touch panel. So that unpacking software, you can see here, the one I was playing with earlier, I put my employee number in. The one I had here is called Ryan 0. It puts the project into the accessible projects folder. That's in a specific Factory Talk View Studio directory. You'll notice I did turn off the sound. Turn it back on and I'll explain why I turned off the sound. Sorry, I kind of skipped over what I did there. I loaded up the interface software, and then I clicked on the Running Man up here. That is the start test simulation or test application. It's going to, what it does is it takes the project, all of these files, it puts them into a local runtime application and then launches the interface just like it would if you were to actually create, like compile that file and push it out to a touch screen. So it allows us to run the simulator here in emulation mode. And we are using, told you I wasn't going to transfer these back and forth, but I guess I lied. We're using the PLC file stations 1 through 8. That's what our simulation program has been used. So we're going to click on that. And you'll probably hear that lovely Windows chime. I find that incredibly annoying, and it happens every time we click on something, and it bothers me. So I muted my remote audio so it stops. So by all means, mute your remote audio, or if you want, you can. At this spot, I get an error code. What error code do you get? These ones down here? On the front? Is it like a box up here? Is it?
Click on that. Yeah. It just shows error all over the screen and blue, everything error.
Okay, yeah. So likely, give me 1 second. Well, you get this. You get these error codes, right? Stuff like that. Is that what it looks like?
No.
No.
You see where it shows time adjust. You see all those blue. Yeah, it just comes up as an error. Yeah.
Okay. So I think, have you downloaded your PLC program yet?
Yeah.
into so I hit X there to close that, and I'm just going to launch it again. So what I did is I think I know what your issue is. I think Vincent guessed, he's guessing the same thing. Is I just deleted the PLC, so there's nothing there. And so does this pop up in the top? And then when you click there, you see all that errors.
Yeah, exactly.
Yeah.
Exactly.
Okay. So that's because the PLC program's not right. So these errors are broken links. Nothing's working. It kind of starts, the process starts to pull its comms driver, which you can see here. It's looking, I'm not going to dig into that. I'll show you what'll happen. So all I'm going to do now is I'm just going to download my program. So this is a program from the D2L. You're going to go open it up, go communications, who's active. We're going to drop down this AB virtual backplane. And then you'll see here that there's actually two processors. We want 0. So that's where the interface is looking for a program, and I'm just going to download our program. You'll see actually over here that this will see that the processor is being downloaded to, or it should, and things will start coming in. So you notice how the animations kind of cleared up. This didn't tell us that it saw the download happening, but sometimes it will. And it fixed up a lot of those issues. So I'm guessing maybe you don't have the processor in the right spot. It's slot 0. Maybe you downloaded the wrong PLC program. I'm not sure, but we can look at that later. So I've downloaded. Your processor starts in program mode. So perfect. So I know we touched this in the fundamentals yesterday, and last week. I think there was a note about it, but we've got 3 main states of a processor. We've got program. So there is a key switch on the front of all processors in some way that will put the processor into program. I want to actually go over. You'll see here this status will be teal or cyan, depending on how your eyes work and what you call it. That means that you can program and make changes to the controller if the key switch on that controller is physically in program, actually pointing to the section of the controller that says program. Some of the newer controllers, it's not a key switch, it's like a physical tiny little switch. If it's in program, you cannot put the processor into run. If the key switch or the switch is in the middle position, it typically points at a remote mode, or called remote service, or remote program, or program access, depending on your different manufacturers. That means that you can get online with the processor and you can program it. So in the middle position, you can actually force it into program mode or into run mode. And that's going to make everything green. It'll say run mode here. The lights on the processor, there's actually a run button. It'll turn green, and that's going to tell you that it's executing code in some fashion. If the key switch is physically in run, oh, you can kind of see it. So if everybody kind of looks here where my mouse is, when I push this into run mode, you see how that actually changed states, and it looks like it's physically pointing at the run. You will see that if you get online with the controller. If it's in run mode, you cannot put it into program mode, and you can only make, actually, you can't even make online edits in run mode. Any questions about that? Anybody get this far and have questions about what we were doing last week? Navigating around. Perfect. Okay, getting on to the lab. So we're going to be adding some logic into the main program and the main routine. So the PLC scans, runs its tasks. We have a main task, and the main task will run until it's completed and then start again. Every time the main task runs, the main routine of the main task. So this one is named main routine, and most of the time it will be named main routine because that's just kind of the way programmers do things. But it doesn't have to be. You can call it whatever you want. Whatever you configure for the program in your main task to be the main routine will be it. You can't change that online. That would be something you'd have to change offline and then download. But just know this main routine isn't necessarily the one named main routine. It's the one with this little plus indicating it's the main routine of that program. And the monitor here, you can watch and see how long scan times take. So the processor is going to go through, run your main routine. Inside this main routine, we have a jump to subroutine, which actually jumps over to R99 simulate, and then it'll run all of this logic. We're going to ignore the logic for today, and we're going to be putting our code changes in main routine, but don't touch rung 0. Don't delete it. You can do your edits above it or below it. It doesn't matter. Just don't delete rung 0 with the jump to subroutine. Other things won't work. So we're going to work in tandem with our graphical interface. We want to create logic where if start push button, this one, is pressed, then light A, which is the light associated with push button A, turns on. Now, there are IO lists and tables, which you got last week, that you can look these things up, or by looking at these tags, I know that input 20 is the push button input for the start button, and the light output is 032. So these are alias tags, and we're going to go right to the outputs. So I want to have a push button turn on a light. So you saw how I added those. So one way to add logic is to work in your palette. Can everybody see this, or is it too small? I'm trying to make things as I don't hear complaints. So here you go. So I dropped my evaluations in there from the palette. Another way that you can make changes is if you're online, you can see this red line is being edited. You can also see that these eyes is being, I forget what I stands for, but it's under construction here. If I double click, it pulls up this text box. So you can also type in the different operands that you want. So XIC is examine if closed. The question mark is the tag, and OTE is an output execution, and the question mark would be its Boolean tag. So if you knew exactly what you wanted, you could type the tag in here and hit enter, and it'll show up. Now this tag doesn't exist, it'll just show up. I know that we want local, and it'll fill in for me. So we want local input 2. So local 2 input data 0. So remember from your controller tags, and again, sorry, if some of you haven't made it through that week 1 lab, that you might not have seen this, but we've got our local IO. So these are your IO cards. Local input, this is the actual input, because we know it is by looking at the digital input tag and the name of the part. Under the input, we have our controller data, and it's a 16-point input. So the first 16 bits of this are our input. So by typing in and knowing that I wanted 20, and in our logic typing in 2i data 0, I will have access to what? I thought I turned that off. Which one? So now when the start button is pressed, local data 2 turns on. So to complete that over here, the same thing, we know we want to go to output here 3.2. So local 3 output data 2. So this rung isn't executing yet. So I could press this. Whoops, I wanted to go the other way. Small. I'm just trying to get everything on the same window for you guys. I could press this and the input's turning on, but because I haven't actually compiled this, it's still under construction. It won't actually execute my code. So the lab says to make a run comment. So by right clicking on this column, you can edit, you can do edit rungs, and you can edit the run comment. The lab asked us to put a comment in that says this button checks if the programmer is awake. So you can see here, my run comment shows up. Now I'm going to compile my edits. So anyone who's worked with Logix 500, if you've made edits in a 500 environment, you have to assemble edits, test edits, and then accept edits, test edits, and then assemble edits. You can go through that step here, accept your pending edits, and then test the edits, and then assemble the edits, and then confirm this again and again. And now the logic is in. And when we push this button, you can see that the output activates, and now the yellow PBA turns on in the interface. If we are making changes to code and you don't want to click a bunch of times, you can actually hit this last button that says finalize all edits in program, and then you hit yes, and it saves you a bunch of clicks. It's really, it's very time saving, but one of the risks of doing that is that if you have edits elsewhere in your logic that you might not want to assemble, it will assemble everything. So if you have changes in one ladder and then you switch over to do troubleshooting or make changes in a different one, this is typically done like if you're commissioning a machine or commissioning a new site, and you're testing one piece of equipment and you're working on code for another one. You could have multiple sets of logic edits going on in your controller, and you want to test and confirm one or two rungs in one subroutine and not the other ones. If you use this like accept all edits, you'll push everything through and it could ruin your day. So for the purposes of the labs, by all means use it. You're not going to break anything. Just be cognizant of it can be bad in the real world. Okay. So the next step is we are going to add in when PBA is activated, light B is turned on. So does anybody want to tell me what I need to do based on how I did that last one? We want PBA to turn on the light for PBB or LTB. So there's a couple things we can do. So we can either start from scratch. So I can create a new rung by hitting new rung, or you can select this rung and copy. So Control C and Control V, just like any other software in the Windows environment, copy and paste. That makes a duplicate of that rung and everything, its comments, everything in its entirety. I know we don't want to necessarily do that all the time, but it'll save us some time, especially we have the structure that we want. Good programmers don't do things again and again, don't build from scratch. So we know we want PBA, so which is I22. So we already have most of the text in here. So there's a couple ways we can just change this 0. So if you double click on your tag, we can go through and edit the text. And now it's pointing at that new point. Or over here, we want this one to be 3, 3. So again, I'll click on it. I'll double click and you see this drop down window. This will open up here. You know what? I'm going to do that in the center. Yeah. So it'll open up a window. A tag. Can I not make you bigger? No. There we go. So now you could actually browse right from here. If you didn't know the name of your tag, you could browse to anything that you wanted that you have access to. So we have access to the controller tags. So those are the tags up here in your controller, but we also have access to main program tags. And these are these in here parameters. So it's not really covered in this lab, but one thing that can be a gotcha is if you have a tag, if you have a controller tag, the controller tag, its scope is global. Does everybody know what that means? So any task, any program. So we have a main task, but we could add additional tasks. We could have a periodic task. We could have an event task. We could also have inside our tasks, we could have additional programs. So I could add in a new program called secondary program, part of main task, and it could have tags. And if I create tags in here, secondary 1, 2, 3, it's a dint, and I want to come over here and use it, I cannot. So let's say I wanted this to be secondary, it won't show up because the scope of the tag is only in the secondary parameters, whereas I can navigate to main program tags. So this is the main program parameters and tags, or controller. So I wanted this to be 1. So we're going for 2, 2. So 2, so card 2, data point, and you've got up it. So you have a dint, but it's only a 16-point card. So all of them can't be used, but we're going for 2. Click on it. It'll put it in there. It does not want a run comment, so we can delete that. And now when we push A, we get B. Any questions? Great. So the last part in the lab, if you've been following along, is one more rung. So I'll show you another way we can add in logic. So by adding in another rung, I'm going to go up here. I'm going to copy this. I'm going to cancel my rung changes because I don't really want to use those change. I don't want to change that rung, but you can't access that text without editing the rung. And I'm going to paste that in here. So just like before, where I copied and pasted the rung with the ladder, the graphical programming interface, I'm just doing this through the text programming interface to show you what that looks like. And we want to have PBB turn on the start push button light. So PBB and is 2 3, and we want it to turn on output 3 0. You can see at the top, as I go through, anybody who's worked in Python or C or any sort of text-based editing, you can see that Rockwell's built in where you type in your command XIC and it'll kind of fill in your syntax beside it. So examine if closed, local input bool, and then output bool and your address. When you're done, go to the end, hit enter. It'll put your ladder rung in, assemble. And now when we press PBB, the start light turns on. So that is the programming portion of this lab, it looks like, or at least the first programming portion of the lab. And the rest of it is filling in some information and some data sheets. So once you finished step 1, step 2 is kind of following along the questions and navigating through your controller tags. So it'll ask you things like, press this button, what happens at this address. So you can see here, when you get into your controller tags, and you can expand them down. So you can see here, you've got these plus marks. So if you want to go to, for example, local input 2 and data, you click on the plus marks and you'll pull down, and this is all your input data. So when we click on, and if you look here, so all I'm doing is I'm clicking on these rows and it's just highlighting information. A good tool for when you're trying to troubleshoot things, or especially if you're working with, let's say, an electrician and they're going through a panel doing IO checks and they're jumping out signals. It's a pain in the butt to just stare at rows and rows of numbers. So by all means, highlight them when you're doing troubleshooting. And we hit the start push button here, and that input turns on. When we hit the stop push button here, well, that input turns off. What input turns off? And you can see it's labeled 2, 1 is off. There's a number of questions to go through and fill out. I'm not going to go through all of those. You can, yeah, I'm not going to go through every single one of those. It's asking you what equipment turns on what based on the information that you can gather from these screens and the IO listings that are found on D2L. I think you can fill out those question marks. And now part 3, an operator can toggle the selector switch to the left and the right when switch A, and that is when switch A, PLC. When switch A is to the right, the lights operate in a new way, which will be defined below. So to make this work, you will need to edit the program and add the selector switch A to your routine. It will need to be added as a branch, which is known as an OR. And the bottom branch will be the new logic. Selector switch A is to the right of the new push button. Selector switch A. So the next logic is looking at selector switch A. So you can see here it's wired to 1, 2, 4. Operator can choose between two different methods of controlling the lights. When selector switch A is to the left, pressing the start push button will turn on light A. So we go to our code. And we know light A is turned on by this output. Sorry, I'm just trying to read this again. When selector switch A is to the left, by pressing start push button B will turn on light A. So when selector switch sorry, I'm trying to. So what we need to figure out first is when selector switch A is to the left, which means when its input is off. So when input 2, 4 is false, so for an OR, when the selector switch is off and push button B, which is PBB, is I 2, 3. Will turn on light A. And now, when selector switch is to the right, start PB turns on the start light. Okay, so I did this earlier and I don't know why it's confusing me now. That's because I have an audience. So with this edit, you can see that when selector switch A is on and we select push button B, this is not true. But when we select start, which is the original condition, it is. When selector switch A is off and we press B, well, now we have an alternate route. Does that make sense? Adding in an or? Okay. So then the last bit I'm going to do here is when selector switch A is to the right, PBB turns on the start light, which already happened. So we know that PBB is turned on. Sorry. The start light is turned on by 3-0. So when the selector switch is to the right, so we know that this tag is the selector switch, but we want to change its condition. So when it's to the right or on and start PB, turns on the start light. So now let's start PB. Turns on the start light, NPBA. Do you see how I added those branches? So double click and you can see here in your tab palette, you've got your different instructions. So if you need to add a branch, you can click somewhere in your rung, add branches. So by clicking here on this rung, you can create parallel rungs down by going branch level. And if you click new branch, it'll create a new OR. So if you had multiple OR statements that were combined with AND statements, you could then start adding in different conditions and evaluations. If you need to duplicate a branch, you can copy and paste and then change the tags on them if need be. Okay. That's most of the lab. There's a couple other challenges that it is asking you to do. I'm not going to go through every single one of them because I do want you guys to struggle's the wrong word, but this is very much a learn by doing. And if you just copy, if you just rewatch the video and copy what I'm doing, I feel like I'm doing you a slight disservice. So I'm going to skip over some of the additional conditions that it's asking you to do for different switch states. But play around with a bunch of different things when you're done. And then there's a PLC challenge here where once you're done, duplicate this. You'll have to look through some of the IO listings for your diversion chute. But remember, everything that's inside this assembly line is just Boolean logic. So this diverter cylinder is just either in one state or another. You've got two different positions. Solenoids are just coils to turn them on. Everything here is Boolean logic, digital inputs, and you can pull up the IO list. Everybody's been able to access the IO list. I don't want to throw this at you guys if you don't have access to that stuff. Has anybody not been able to download the stuff from D2L? Okay. So when you're done with your program, you're not, I'm just confirming we're not making changes to the, yeah. So we're not making any changes to the simulation graphical interface. So I'm shutting that down. So when you're done with your program, save it as whatever it's telling you to, saving it as a, so I'm just trying to confirm what they're getting you to submit me, if it's just the report or if it's the printout. Yeah, I would prefer it if you could get me both of them. So save your file. So file, save as, and put your name in it. And then copy and paste it off of these machines onto your personal desktop to submit that in the Dropbox. But it's also asking for generate report. So this is a neat feature. It's used, I've used it fairly infrequently in industry, but sometimes if you need to print out your logic for whatever reason, this is how you do it. So it goes step by step, and you can unselect everything that you need, that you don't need, and then expand out. Again, you can see with your tree here, and select main routine. And then select print. And then, yes, cool. It sees that. I can print right to my printer. So my home printer is named Mr. Printer because I don't know. It's embarrassing. You guys know that now. But you guys can PDF it. Where is it going to save that though? What's redirect to? It specifically says to go to, again, I'm following through this, redirect to. Wow, I am impressed. So that put that right onto my host machine. Yeah, okay. So yeah, just submit the PDF. It'll have everything that you guys needed to do. And that'll be good. I don't need your PLC programs. And that's the lab. I skipped over a few parts of it, but it's really read what it's wanting you to do with the specific inputs and outputs and what it's wanting you to turn on. And then if you want to try the challenge, challenge yourself. As cliche as that may sound, programming is a skill you will develop more as you program, if the just like anything else. So the more things you try, even if they seem complicated, it's just keep trying new things or repeat the lab. Yeah, and if you've got any questions, by all means ask me and I'll help you troubleshoot as much as I can for the next hour. Yeah, a little more than an hour. So is everybody good? Any questions? I'm gonna kind of let you guys, if we do it in a different, sure, yeah, do that.
Hey Ryan, sorry, this is Eddie.
Yeah.
So is the expectation that we only submit the PLC challenge one, or do we do the whole, all the requirements for task
lab.
one, task?
The
whole-
task 1, task 2, and let me look at the rubric, because I was under the impression that the challenge was optional, but I don't want to say that if it's graded. It is, yeah, it is graded.
So
There is one extra point available for trying the PLC challenge.
one of the things is that obviously the chat. I mean, I'm assuming that like part F is just like you just basically want rungs. You don't want it to be you don't want it to show animation or something as such, because for something like push buttons, you almost have to like, because the PBA and start push buttons are momentary switches, right? They're momentary buttons. So to see some form of animation, technically need to hold both of them. So I'm assuming it's just that, or is it that you would like to see animation? Like if we make the code, would you like to see animation or something like that? Or is it just like
I
rungs?
don't need to see the touchscreen, because you're right. You can't press both of those buttons at the same time unless you've got a touchscreen, but you're not submitting the interface.
And is it okay if we have all the parts, including the challenge, on one basic on a single main routine, or do you want it separate main routines?
If you're gonna submit it in a single routine, in a single report, try to add in some rung comments so they're just separated out.
Okay.
Or Vincent asked the same thing. If you want a separate submission, if you want to do that, a second PDF is fine. I believe it's just a Dropbox. Did everybody was everybody okay who did submit the PNGs finding the Dropbox? Say silence is yes. Okay. It looks like Martin, you submitted your last week's lab in this week's lab. And I can't move it. So I don't know. I think I can grade it. If you submit this week's in there as well, I'll just look at this one and grade only this one and ignore last week's. Yeah. I will be here. If you guys want to get working on your lab, if you've got any questions, I'm going to work on looking at your quizzes from last week. So yeah, let me know if you have any questions. I'm going to go on mute.